then after conservation of energy, is there any need of any other law? And if so, then why we need those other laws like second law of thermodynamics? Because we know that conservation of energy is a very powerful law and it can almost answer all the questions in mechanics. You can apply conservation principles and find the solutions. Then what is the need of second law of thermodynamics? Let us consider a situation in which we consider there is a container whose boundary is an adiabatic wall. Adiabatic wall means there is no heated exchange of energy, heat energy. Adiabatic wall means no exchange of heat energy takes place from this container. Now we consider that this container is divided into two parts by a diathermic wall, like this. Into two parts, this wall is given diathermic. Means from this portion to this portion, heat energy can be exchanged. But we consider both the system are closed system, that means no mass can be exchanged between these two. And by this adiabatic wall, we consider that this one is an isolated system and heat and mass, nothing can penetrate this adiabatic wall. And only this one is a diathermic wall which we consider heat can penetrate but mass cannot penetrate. Now in this situation, suppose there is a object 1, there is a system 1, there is a system 2. And suppose the system 1 is at temperature T1, system 2 is at temperature T2, and it is given that T1 is greater than T2. Then in which direction heat will flow? From 1 to 2, penetrating this diathermic wall. How long it will flow? Until both have the same temperature, that is thermal equilibrium is reached. Up to that, heat energy will flow from system 1 to system 2. Now initially they have temperature T1 and T2 and they have certain amount of energy, total energy. Then after the equilibrium is reached, both have same temperature, but is the total energy of the system, two component system, changes from the previous value or it will remain same? Because no energy can escape from this adiabatic wall. Remember, means we can say that total energy when this system is at temperature T1, this one is at temperature T1 or something, say Q, and after the settlement of thermal equilibrium, the total thermal energy will remain Q. That means total energy remains same, but now the temperatures are same, that means entire system is in thermal equilibrium. Now think about it. If it happens that heat is flowing from system 2 to system 1 instead of 1 to 2, such that one time will come when entire heat from this one will travel to this one. So what will happen? T1 will rise and T2 will decrease further. But is the total energy of the entire two system is changed or remain same? Remain same. That means whether heat is flowing from high temperature to low temperature or from low temperature to high temperature, that does not violate conservation of energy. That is first law of thermodynamics. So heat can flow in either direction. If you put two bodies of different temperature together, if the heat flows from high temperature to low temperature, normally we see that conservation of energy, that is thermodynamics first law, is valid. Then if the converse is true, that means whenever we put two bodies together, heat is traveling from low temperature to high temperature to make the high temperature more higher, to make the low temperature more lower, still thermodynamics first law is not invalid. So first law of thermodynamics permits both. But what we see in nature is the second process occurs, that whenever we put two bodies together, hot body becomes more hotter and cold body becomes more colder. No. So there is the tendency to travel towards the thermal equilibrium. But if there is no tendency to go towards the thermal equilibrium, even in that case, thermodynamics first law is valid. Means the flow of the spontaneous flow of heat transfer, spontaneous direction of heat flow cannot be determined by first law of thermodynamics. What will be the spontaneous direction? Spontaneous direction is from high temperature to low temperature. So this spontaneous direction of heat flow cannot be determined by first law of thermodynamics. First law of thermodynamics is saying that heat will flow, total energy remain conserved. But in which direction? High to low or low to high? There is no restriction imposed by first law of thermodynamics. So that's why to define the natural processes, what will be their spontaneity, we require second law of thermodynamics. Okay, first law define conservation of energy, but it cannot say about what is the spontaneous direction of flow of heat when two systems put together. So that spontaneity is defined by, direction of spontaneity is defined by second law of thermodynamics. That's why second law of thermodynamics is required. Clear? Now, there are two statements of second law of thermodynamics, or two procedures to study second law of thermodynamics. One is the formal development of the second law of thermodynamics, which was initially discovered by the discovery of heat engines, like steam engine, reverse heat engine, refrigerator, and different other heat engines are there. So there is a version of heat engine version of thermodynamics second law, and after that a crucial thing, entropy, was discovered by Clausius, and that is the mathematical part of the second law of thermodynamics. So first we will discuss the heat engine portion of the experimental version of the second law of thermodynamics. Write down the first one. First statement is called Kelvin-Planck statement. Kelvin Planck statement. Second one is called Clausius statement, second law. Okay, just write down the first law, Kelvin-Planck statement. It is impossible to construct a device, it is impossible to construct a device operating in a cycle. It is impossible to construct a device operating in a cycle whose sole result is to transfer heat, whose sole result is to transfer write down whose sole result is to produce a mechanical work, whose sole result is to produce a mechanical work. Write down whose sole result is to produce a mechanical work in a complete cycle, in a complete cycle by exchanging heat, by exchanging heat with a single heat reservoir, by exchanging heat with a single heat reservoir. Okay. It is impossible to construct a device operating in a cycle whose sole result is to produce mechanical work by exchanging heat with a single reservoir. Second version, that is the Clausius version. Write down, it is impossible to construct a device, it is impossible to construct a device operating in a cycle whose sole result is to transfer heat, from low temperature to high temperature, from low temperature to high temperature spontaneously. Low temperature to high temperature spontaneously. Okay. Now see what this laws want to tell.
Let's go.
First one, heat reservoir. Heat reservoir means a source of heat which is always at a fixed temperature. Its temperature will not change if you draw some amount of heat from it or if you give some amount of heat to it. That is called a heat reservoir. Like ocean. If you take 1 cup of water from ocean, will that amount of water of ocean will change? No. So the same thing. So heat reservoir means you can consider like a heat ocean. So if you are taking some amount of heat from it or given some amount of heat to it, its temperature will not change. Suppose I am considering a candle. If you take any other stick and burn it in the candle and take it outside, will you say that candle flame's temperature will change? No. That means it is behaving like a heat reservoir. So we consider 2 types of heat reservoir. One is this one, 2 heat reservoir is there. One is at temperature T1. We consider another heat reservoir at temperature T2. And it is given that T1 greater than T2 means it is the high temperature reservoir or hot reservoir. It is the low temperature reservoir called the sink, and this is generally called source sink. High temperature reservoir, low temperature reservoir. Now, so you have to prepare a device that is operating in a cyclic process, means over and over it can do the same process. And this type of device is called a heat engine. And what Kelvin-Planck statement is saying, suppose this heat engine draws an amount of heat here from high temperature reservoir, let it be Q1. It cannot completely convert it into work, mechanical work. It cannot be completely converted into mechanical work. So that is given in the statement. What Kelvin-Planck is saying, it is impossible to produce a mechanical work in a complete cycle by exchanging heat with only one heat source, only one reservoir. Means this is only one reservoir, it is exchanging heat with it and producing mechanical work in a complete cycle. It is not possible. Then why not possible? Because some amount of heat it must be rejected at the low temperature reservoir. Means whatever it will draw, it will reject a portion to the cold reservoir and remaining amount is converted to the work done. Mechanical work can be produced by the remaining amount. Always there will be some loss. So it has to reject some amount of heat to the low temperature reservoir. It cannot convert the entire heat to the mechanical work. There is always certain amount of loss. Clear? Loss will be there. Means 100% conversion is not possible, as Kelvin-Planck statement is saying. Now, what is a proper example of this? Just a steam engine. Whenever there is a water in the boiler, so you are supplying heat energy, so it will draw heat in a cold water will draw the heat energy from the heat reservoir, suppose at temperature T1. So the steam water is converted to the steam, and as a result it exerts pressure on the motor, and as a result there will be mechanical work and steam engine will move. But see, in the entire process, the chamber of the boiler, entire water, all these things, temperature will increase. So the heat energy drawn is partially converted to work done, and remaining part is used to increase the internal energy of the water and the boiling chamber and all these things. So 100% conversion is not possible. So some amount of heat energy is given to the low temperature. Means if the boiler is heated up, then this heat is going to the environment, and environment is a low temperature reservoir, that is a sink. Now this is the normal operation of a heat engine as predicted by this. Heat engine can be prepared, but its opposite cannot be prepared, where Q2 equal to 0. Means entire thing cannot be converted. That is given by Kelvin-Planck statement of second law. Now we come to Clausius statement. Clausius is talking about something else.
Sir.
Suppose this one is a high temperature reservoir, this one is a low temperature reservoir.
Okay.
And there is a heat engine. Can this heat engine draw a certain amount of heat from here and transfer it completely to high temperature in a complete cycle? Clausius is saying that this cannot be done. This cannot be done. It will extract some heat from low temperature and transfer heat this to the high temperature spontaneously. That is not possible. So So this type of heat engine cannot be prepared. But if we supply mechanical work to this engine, then it can do it. And if you supply mechanical work, means you are forcing, so it is not a spontaneous work, it is forced work. So if you give some mechanical work to this, say W, then it can transfer Q2 plus W something, or we can consider Q1 amount of it, different amount of it will be transferred to T1. But you have to provide this W. Now what is an example? So this is not a normal heat engine, because normal heat engine is drawing heat from high temperature and producing mechanical work by rejecting something to the cold temperature, low temperature. Now this one is doing the opposite operation. It takes as an input mechanical work, draw some amount of heat from the cold reservoir, so temperature of the cold reservoir drops more and temperature of the high reservoir you can consider to be increasing, but since they are reservoir, the temperature will not change at all. So heat is rejected, heat is given to the high temperature. Now this one is not a normal heat engine, it is doing the opposite of the normal heat engine. So we write RHE, that is called a reversed heat engine. Reversed heat engine, not reversible. All these engines are reversible because they are working in a cyclic process, it is mentioned. This is called reversed heat engine. What are reversed heat engine? Refrigerator, AC machine, all these are cooling agents are reversed heat engine. Now, if I consider this one is your room, this one is your room, then the entire room cannot be considered just like a reservoir that its temperature will not change if we extract heat or given some amount of heat to it. You can consider the entire environment of this earth as a reservoir. But for this room, can we completely consider that it is just like a reservoir, that if some amount of heat is given to it or extracted from it, its temperature will remain same? No, because if you switch on the AC machine, it will actually suck heat from the room, absorb the heat from the room and deliver it to the outside. Because if you are standing in front of the outdoor unit of AC, the fan is rotating and you will feel hot air is coming. Means from the room it is actually extracting heat energy, and room is not that much big such that you can consider it completely as a heat reservoir whose temperature will not change. So temperature of the room drops and it will deliver this heat energy to the outdoor unit. Suppose in the daytime inside this room, suppose temperature is say 40 degrees Celsius, and outside in the scorching heat of sun the temperature may be 45 degrees, 5 degree more, 45 degrees Celsius, and now you close all the windows and everything and switch on the AC machine. What will happen? After some time it will extract heat from your room, so the temperature of the room will drop, because inside the room the environment is not like a very big ocean of heat such that some amount of heat is extracted but temperature will not change. That is not that much vast, the room, inside the room environment or air. So then we can consider that this heat energy is extracted, so the temperature of the room will drop, and AC machine will convert this one, transfer this amount of heat extracted to the outdoor unit where it is given to the, it is rejected to the atmosphere. Okay, so that atmosphere can be considered as a very large ocean of heat, and some amount of heat given by your AC machine to the atmosphere will not appreciably change the temperature of the atmosphere. But nowadays it is a problem because everybody is using AC machine, every room, everywhere there is use of AC machine. So together they are producing so much heat energy to the atmosphere that global warming is another problem now. Now we will consider that can the AC machine transfer the heat, extract the heat energy from the low temperature and transfer it to the high temperature on its own? Then you don't have to pay the bill, electric bill, if it is. But we have to pay the electric bill, means the electrical energy should be provided. So this electrical energy is this work done, which is given to the AC machine. Then AC machine can extract heat from the low temperature and transfer it to the high temperature. Okay. Now, Clausius is saying that this is possible, but W0 still it transfers, that is not possible. Means spontaneous, it will not be a spontaneous process. It will be a forced process. You have to supply any other form of energy as a mechanical work to run the AC machine. Then AC machine can transfer it from low temperature to high temperature. Spontaneous transfer is not possible from low temperature to high temperature. Clear? Now, are these two laws saying different thing or they are saying the same thing? Are these two versions of the second law saying independent thing or they are saying the same thing? They are saying the same thing. How? Achha, suppose in this room all of you are given some exam, not a MCQ exam. Suppose it is descriptive exam like your board exams. Okay, and you are sitting according to your roll number. Now, suppose after checking the copies, it is found that these two copy are exactly same. Exactly same means they are writing the correct answer. Suppose for question number 1, question number 2, question number 3 and question number 6, 7. Both of them have written the same answer, identical. And both are correct. What the teacher will say? Teacher will say nothing. He can doubt, but he cannot say firmly that no, you are copying this one, you are cheating in this exam. Teacher will not say this. If both are correct, both answers, if the answers are correct, then teacher will not blame that much. But if the answers are wrong and same types of mistake is written in the paper, teacher will definitely say, okay, you are cheating, someone of you copying from the other. Means, if I consider any one of this statement is violated, I can show you the other statement is already violated. Means they are interrelated. Because if they are both true, it can be true independently. But if the violation of one implies the violation of other, that means they are interrelated. There is no doubt about that. So I consider that there is a violation of Kelvin-Planck. Entire energy is utilized in work done by this heat engine. So with how much reservoir this heat engine is dealing with? 1. It is not dealing with the cold reservoir. It is only dealing with the hot reservoir and producing a mechanical work. So this is a violation of the Kelvin-Planck statement, because Kelvin-Planck statement said that this kind of heat engine cannot be prepared. So we consider here a violation of the Kelvin-Planck statement. Now, for the working of reversed heat engine, what we require? Some mechanical work. Without giving mechanical work, reversed heat engine will not extract heat from the cold reservoir and transfer it to the hot reservoir. So I consider, okay, fine, this W equal to Q1, so we will use this power, this work done to run the reversed heat engine. We consider this heat engine, it will producing some mechanical work, and using that mechanical work, we will run this reversed heat engine. So we connect this output of this heat engine to the input of the reversed heat engine. Now, what it will do? It will extract Q2 from here and transfer this one to transfer Q1 amount of it to hot reservoir. Now consider these two together. So these two together produce a single device which is extracting heat from which one? Cold reservoir, and transfer it to the hot reservoir. Okay? Is there any external source giving energy to this? No, because together they are constituting a single system. They are not requiring any external source to be given energy to this, to transfer heat from the low temperature to high temperature. Means these two together is a device which will transfer heat energy from the low temperature to the high temperature without any external work done, means spontaneously, and that violates the Clausius statement. Together this engine and this engine constitute a single device which is extracting heat from low temperature and transfer it to the high temperature without taking any amount of work done from any external agent. That you cannot do. Means you are saying, okay, I will switch on the AC. The AC will do its normal work because from the outdoor of the AC, the outdoor fan of the unit of the AC, the heat energy that is rejected, I will take this heat energy to run the AC and will not pay the bill, electric bill, because I will disconnect it from the electric supply and I will run the AC, and whatever heat is rejected from the outdoor unit, I will use that heat to run the AC again. So means it is a cyclic process. You are claiming that AC will run without paying the electricity bill. Is it possible? No. So now the violation of the Kelvin-Planck is the violation of Clausius statement also. Clear? So both the test statements are connected. Now, then different types of heat engines that we have discussed here. One is normal heat engine, another is reversed heat engine, and now other two types of engines that we will discuss. One is generally called the irreversible heat engine and another is reversible heat engine. What all this name means? Normal heat engine means heat engine. This term means it will draw heat from hot reservoir, produce a mechanical work in a complete cycle and reject some amount of heat to the cold reservoir. That is the heat engine. Now, heat engine can be of two types. One is following a reversible process, another is following irreversible process. Following reversible process, following irreversible process. Similarly, reversed heat engine, extracting heat from the cold reservoir, transfer an amount of heat to the hot reservoir by taking work as an input from other source. That is called a reverse state engine. Again, reverse state engine can be of two types: reversible, irreversible. Because whether the process is reversible process or irreversible process. Suppose normal AC machine, is it a reversible reverse state engine or irreversible reverse state engine? Irreversible, because the coolant gas will finish after some time. After some day, the coolant gas R32 that is used as a coolant, so that coolant gas will be finished. Then you have to refill the gas again, otherwise AC will not work. So if after each and every part, every running of AC, coolant gas will be in the same amount, then it will be reversible, but it is not reusable. It will finish and you have to refill it. Now we will discuss this one, that which engine is most efficient. First of all, think about it. Reversible engines are always more efficient than any irreversible engine. Reversible engines are always more efficient than the irreversible engine. Irreversible means the working substance will not be in the initial state again after the complete cycle. It will be in a different state. So irreversible engine's efficiency is always less than reversible engine's efficiency. Now, can we prepare a completely ideal engine whose efficiency is maximum? That is one. I want to prepare ideal engine. Ideal engine means all steps are ideal steps. Now let us consider, in searching of that, we will consider this one. A working substance is taken which is an ideal gas. Remember, working substance is ideal gas. Okay. Now we consider that it is following this type of a cyclic process. So initially it is at P1, V1, T1. Initially the ideal gas is at a state defined by P1, V1, T1. Okay. Then it is taken here at P2, V2, T1. I consider this is A, this is B, this is C, this is D. P2, V2, T1, not T2. Now see the diagram. A to B. This process is which process? Isothermal. It is isothermal expansion. Isothermal expansion of the gas. Temperature remains same, but volume is increased. Pressure decreasing, volume is increasing. So first step A to B is an isothermal expansion. Okay. Then B to C. Pressure is P3, volume is V3, temperature is considered to be T2. P3, V3, T2. Now see, this B to C has more slope than A to B because it is steep, means it is adiabatic process. So B to C is an adiabatic expansion. See, volume is increasing, but it is very sharp. So it is called adiabatic process. Because the other day we have discussed that slope of isothermal curve and adiabatic curve slope is gamma times larger than the gamma times the slope of isothermal curve. Okay. So that's why P3, V3, T2 is taken. This is adiabatic expansion. B to C, adiabatic expansion. Then C to D, I consider it is P4, V4, T2. That is isothermal compression. Isothermal compression. Okay? Because volume is decreasing but slope is low. So that is isothermal compression. Finally, it is taken to D, from D to A. D to A means volume is decreasing but it is steeper, means adiabatic compression. So fourth step: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression, and system is taken to the initial state again, means the process is cyclic. So it is taken back to the initial state, means the process is cyclic. And in cyclic process, what is the change in internal energy? Zero. Change in internal energy will be zero. Now, if this one occurs, then can we say that whatever be the amount of heat energy, given to this engine which is operating in this process, it will utilize all this energy to produce the mechanical work. In that case, what will be its efficiency? 100%. But we will show that even this ideal engine, most ideal engine, cannot have 100% efficiency. All steps are ideal, isothermal, adiabatic, all these things. Still, it is lacking from the 100% efficiency. See how. Then, in which step heat energy will enter this system? This one. Working substance is the system. In which stage heat energy will enter? A to B, because that is isothermal expansion. Isothermal expansion means temperature remains same, but heat energy can go in, and heat energy goes and it will produce mechanical work. So volume will expand and it is doing mechanical work. So that is an isothermal expansion. So this working substance, this ideal gas, will absorb energy Q1, suppose, at temperature T1 when it is following an isothermal expansion. Because isothermal expansion means gas will expand keeping its temperature constant. Means whatever be the heat energy you have to supply, it will entirely utilize to increase the volume such that work is done by the gas. Okay. Now, in which step gas will reject heat energy to the surrounding? Isothermal compression. Compression means gas will contract, means it will release heat energy to the atmosphere. T2, Q2. But see, in process BC and process DA, no heat energy can be exchanged because those are adiabatic processes. In adiabatic process, there is no exchange of heat energy between system and surrounding. Okay. So how much heat energy it is absorbing? Q1, and rejecting Q amount of heat energy? Q2. So following the process of a heat engine as predicted by Kelvin-Planck, it will do some mechanical work with Q1 minus Q2. It is doing some mechanical work with the energy Q1 minus Q2.
They can distribute.
So efficiency is determined by work output by heat input. Output by input is called the efficiency. Substitute W by Q1. It is Q1 minus Q2 by Q1. So it will be 1 minus Q2 by Q1. 1 minus Q2 by Q1. Now, if you supply heat energy to a system, its temperature will increase. So can I write that Q is proportional to T? If you supply heat energy to a system, then its temperature will increase. So from that logic, can I write Q proportional to T? Because if you supply more heat, its temperature will increase more. So we can write that Q1 by Q2 equal to T1 by T2. Actually, you cannot write like that. You have to write that Q is a monotonic increasing function of temperature is a monotonic increasing function of heat energy given to the system, and then we can conclude this one. But all these things are not required. You can simply write that Q1 by Q2 equal to T2 by T1 by T2, and substitute this one 1 minus T2 by T1. Now check which one is more, T1 or T2? Because T1 is high temperature, T2 is low temperature. So from high temperature reservoir, it absorbs heat Q1 and reject heat Q2 to the low temperature reservoir. So T2 is greater than T1, but T1 is greater than T2. T1 is greater than T2. So T2 by T1, this ratio is less than 1, and 1 minus something. 1 minus something is less than 1, means efficiency, this value is always less than 1. So we can predict that eta less than 1 because T2 less than T1. So this most idealized heat engine is also not having efficiency 100%. This is the most efficient engine. This is termed as Carnot engine. The spelling is not, pronunciation is not Carnot. T is silent. Carnot engine. So even Carnot engine has efficiency less than 100%. Then all the reversible engines have efficiency. All the reversible engine that we can prepare in reality is not by following any ideal step, because in reality ideal steps will not occur. So all reversible heat engine have efficiency less than Carnot engine, and all irreversible engine has efficiency much less than that. So nothing can prepare by no means you can prepare a heat engine which is 100% efficient. Okay, now After this Carnot engine, so whenever we will discuss in ideal steps in thermodynamics, we will consider this concept of Carnot engine, that is the maximum efficient reversible heat engine. Now, can you achieve, what is the absolute zero temperature? What is absolute zero temperature? Minus 273 degrees Celsius. Strictly speaking, minus 273.15 degrees Celsius. And that is considered as the 0 Kelvin. See here, all the things are written in Kelvin. Okay, so if you try to calculate efficiency and put these quantities in centigrade, it will not give you the correct answer. You have to put it in Kelvin. T1, T2. These are in Kelvin. Now, absolute zero can never be achieved experimentally. Can never be achieved experimentally. Why? Why you can never experimentally reach to absolute zero? Even if you are supplied with a best cooling device, still you cannot get absolute zero. What cooling device will do? It will extract heat from the low temperature and transfer it to the high temperature. So low temperature will decrease more lower and high temperature will be more higher in this situation. Now think about it. To get absolute zero by a cooling machine, suppose AC machine or refrigerator or anything, what will be the final temperature of the lower reservoir? Absolute zero. That should be T2 equal to 0 Kelvin. T2 equal to 0 Kelvin. Just, and what is the maximum efficient heat engine that you have ideally? Ideally, this Carnot engine, put T2 equal to 0 Kelvin. What it will give? 1. But earlier you commented that even Carnot engine have efficiency less than 100%. So even Carnot engine is not sufficient to cool any room or anything to the temperature of absolute zero. So other heat engines have efficiency less than Carnot engine, so they can never help you experimentally to get absolute zero. So absolute zero is a theoretical concept. You can never reach absolute zero in reality, because thermodynamics second law is putting a barrier. Means to get absolute zero by cooling, you require a heat engine which has 100% efficient, and all the heat engines that we have much less efficient than even the Carnot engine, and even Carnot engine is not 100% efficient. Most ideal step is not 100% efficient. Then how can you say that I will experimentally find absolute zero? It's not possible. Okay. Now, one question. Just see the efficiency of the Carnot engine. This form. If I increase the temperature of the hot reservoir, if I increase the temperature of the hot reservoir, then what will happen to the efficiency of the Carnot engine? Will it increase or will the efficiency decrease? Means T1 is increased, keeping T2 fixed. T2 fixed, T1 is increasing. Hot reservoir will become more and more higher temperature. What will happen to eta? Will it increase or decrease?
And what's that happen?
Increase, because as T1 is going to increase, this T2 by T1 factor will decrease. So 1 minus T2 by T1 factor will increase. So there is an increase in efficiency, right? So if cold temperature reservoir, low temperature reservoir remains same at same temperature, and we increase the temperature of the hot reservoir, then efficiency of the Carnot engine working between these two reservoirs will increase. Say someone chooses a different method. He considered that I will keep T1 fixed and decrease the temperature of the low temperature reservoir. That is, cold reservoir is making more cold. In that case, efficiency will also increase. T2 is decreasing, keeping T1 fixed. So this factor is decreasing. So 1 minus this factor will increase, and as a result efficiency will increase. So there are two procedures to increase the efficiency of a Carnot engine. Either you will decrease the temperature of the cold reservoir, or to increase the temperature of the hot reservoir. Now you have to tell me which one is more efficient, which one is better.
Yeah, that.
Acha, write down the question. We can increase the efficiency of a Carnot engine. We can increase the efficiency of a Carnot engine by either increasing the temperature of hot reservoir, increasing the temperature of the hot reservoir by T Kelvin, capital T Kelvin, or by decreasing the temperature of the cold reservoir, or by decreasing the temperature of the cold reservoir by T Kelvin. Same amount, increase or decrease by T Kelvin. In which process efficiency will be increase more? In which process efficiency will increase more? This can come as a MCQ also. Suppose in first process it is given eta 1, in second process it is given eta 2, and say it is given that eta 1 greater than eta 2, eta 1 less than eta 2, eta 1 equal to eta 2, something. There's options, and you have to choose the correct option.
Thank you.
T1, T2 is also increased. But
No, T2 remain fixed.
What?
So while we are changing one, other remain fixed. That is mentioned in the question.
So,
Either or, either you increase T1
yes.
or decrease T2. Your answer is correct. Either you have to increase T1 or you have to decrease T2. These two options are given. Now which one between them will produce more efficiency?
And he said that can't be the first to go.
A simple, very simple calculation. So I consider that if I change T1, then new efficiency will become eta 1. Then what will be its 1 minus T2 by T1 plus T Kelvin?
Good.
Means low temperature reservoir is untouched, only we increase the temperature of the hot reservoir by T Kelvin. So new efficiency will become eta 1. So what is eta 1? We can calculate eta 1 equal to T1 plus T, then T1 plus T minus T2. Okay, this is my first equation. In the second process, what we have to do? Consider the efficiency to be eta 2. It will be 1 minus T2 minus T by T1. So now low temperature reservoirs is decreased to by T, but hot temperature remain same. So we consider the new efficiency prepared in this way will be eta 2. Then again calculate. Eta 2 will become T1. So T1 minus T2 plus T. Minus T2, minus plus, so it will be plus T. Okay. Now divide these two. What you will get? This is equation 2, this is equation 1, divide these two result. See, numerator is same for both. T1 plus T minus T2, T1 plus T minus T2. So numerator will cancel. So if you divide these two, you will get T1 by T1 plus. Which one is greater, numerator or denominator? Denominator, because there is additional term T. So I can write that eta 1 by eta 2 is less than 1, because right side is T1 divided by T1 plus T. So denominator is more. So eta 1 by eta 2 is less than 1, implies that eta 1 less than eta 2. Means if you decrease the temperature of the low temperature reservoir further, then efficiency will increase more. In both the process, efficiency will increase, but it will increase more if you decrease the low temperature to further lower, not the high temperature to further higher. Okay. Now, one more thing that we will discuss here. Sometimes you find this type of a problem that PV to the power 3 equal to constant, it is given. So whenever you get this type of a problem, it is showing some adiabatic process. You have to consider that PV to the power gamma equal to constant and compare this, then you will find gamma equal to 3. Okay, sometimes you will see this type of a equation given. It is given that Pt cube equal to constant. And the question is find the value of gamma. What you will do? It is given that for a particular ideal gas, Pt cube equal to constant. Now, you have to find the value of gamma. Don't write P to the power gamma and say gamma is again 3, because gamma is the power of V, not the power of T. So you have to convert this given equation in PV form, eliminating T. Since it is ideal gas, it is obeying equation of state of the ideal gas, and equation of state of an ideal gas says that PV, suppose 1 mole we consider, it is RT. Just from this write T. T will become PV by R. Okay? Substitute it in this equation. Then you can write P, in place of T I will write T P cube V cube by R cube, that is equal to this constant, suppose C. Okay, then you can write this equation as P to the power 4 V to the power 3, this is equal to R cube C. This is equal to R cube C. Then you have to take to the power 1 by 4 on both sides, because I can write this one as P V to the power 3 by 4 equal to R cube C whole to the power 1 by 4. Okay, to find the value of P to the power 4 is there, then to find P we have to take to the power 1 by 4 on both sides. So it will be P into V to the power 3 by 4 equal to R cube into C to the power 1 by 4. Now check, R cube into C, this one is to the power 1 by 4, this entire thing is constant. So we can write now P V to the power 3 by 4 equal to constant, and now we can compare this equation with this form and write gamma equal to 3 by 4. So whenever this type of equation is given, PT or VT, don't get confused. Convert using ideal gas equation to PV form and then compare. Otherwise, if you can remember the adiabatic process law in terms of TV or in terms of PT, from that you can do. But otherwise, if you remember only this format, P V to the power gamma equal to constant, then whenever other variables are given, convert it into that PV form equation and then compare. Don't write that T to the power 3 is there, V to the power 3 is there, so gamma is 3. No. P to the power gamma, V to the power gamma and T to the power 3 cannot be equated.
Gamma is always greater than
I taken just example. And one more thing, that is sometimes you find this type of a relation Cp by Cv. Cp by Cv, which is called gamma. And gamma can be written as 1 plus 2 by F. Gamma equal to 1 plus 2 by F. This type of a relation is given, and sometimes it is asked that find the value of gamma for a diatomic gas. What will be the value of gamma? 3 options are given.
Okay.
Now, how you can proceed to this? Now, what is this F?
What? Yeah.
F called degrees of freedom. Degrees of freedom means what do we mean by degrees of freedom? Suppose I consider one molecule of an ideal gas. One molecule of an ideal gas. What will be its degrees of freedom? 3. Because minimum number of coordinates necessary to specify the position of a molecule, that is called the degrees of freedom, or minimum number of number of independent coordinates, minimum number of independent coordinates necessary to specify the configuration of a system, that is called degrees of freedom. Now, if I consider a single molecule system, its degrees of freedom can be X, Y, Z, nothing else. Now, if I consider two molecules of an ideal gas, what will be its degrees of freedom? So, for single molecule of an ideal gas, degrees of freedom is 3. For 2 molecules of an ideal gas, what is the number of degrees of freedom? What?
Oh, it's 5.
5. Wrong. It's 6. Achha, okay, for 3 molecules of an ideal gas,
What makes you say the chance behind
what?
that?
9.
Right.
Again wrong. I said ideal gas. Ideal gas means there is no intermolecular attraction. So every molecule can go freely over and over. So each molecule is identical. So if one molecule has 3 degrees of freedom, 2 molecule has 6 degrees of freedom, 3 molecule has 9 degrees of freedom. But if there are restrictions given, ideal gas, there can be no restriction because there is no intermolecular force. You forget this. I mentioned ideal gas. Now if it is not ideal gas, then 2 molecules, and if we consider that molecular distance is fixed, it is not an ideal gas, then we can consider that the molecular distance is fixed. It is another assumption. Then what will happen?
What is it?
This distance is fixed now. How many degrees of freedom it has? Now 5. Because this one, we can say, to represent this one, 3 coordinates are required. Suppose x1, y1, z1. For this one, how many required? x2, y2, z2. But now there is a restriction that x2 minus x1, this is equal to, suppose, some n which is constant. So I can as well like this x2 as x1 plus l. So how many independent coordinate you require? 5. 1, 2, 3, 4, 5. Because x1 is already determined. Now you require 5. Because you restrict the motion in one direction by saying that their distance, intermolecular distance is fixed, and that can only happen if they are attracted by certain force, that is intermolecular force. If intermolecular force is not there, then they can free to roam anywhere. Then what will be the number of degrees of freedom? 3 plus 3, 6. Intermolecular force has to be present to decrease 1 degrees of freedom.
What is
Because this marker, if you consider this end of the marker is a point, this end of the marker is a molecule, and remaining part is a not a massless rod whose length is fixed. In this situation, whatever, anywhere this marker can go in any orientation, but the distance between these two molecules will not change. So each point particle in space have 3 coordinate axis required for its specification. So 3 plus 3 6, but there is a restriction that its length is constant. So you can always decrease 1 coordinate. So 6 minus 1, that is 5. Clear? So for a diatomic gas, degrees of freedom will become 5. Because the gases that we normally found in reality, these are not ideal gas. There is intermolecular attraction between them. Now, if I consider a triatomic gas, and then if it is ideal, nothing else, each molecule can move. So its degrees of freedom for 3 molecules, if it can move independently, it has 9 degrees of freedom. But if it is a triatomic real gas like, then what will be the number of degrees of freedom? What? It may be 7, maybe some other one, maybe 6. It depends on the arrangement of the molecules.
What?
See, these 3 distances are fixed. Now if this kind of situation is there, then for each molecule there is 3. So how many molecules are there? 3. So you can write 3 into 3. How many restrictions are imposed? So 9 minus 3, that is, but it can be arranged like this also, linear chain. In that case, it will decrease to 7 because 2 restrictions will be there. So it will decrease to 7. It may be linear chain, it may be closed chain. It depends on the arrangement. And for higher molecules, there are more complicated structure, more variations will be there. And one more thing, that is equipartition of energy. It is said that for an ideal gas you can consider that total energy is distributed, total kinetic energy is distributed among all degrees of freedom equally. It is equally distributed between its all degrees of freedom, and for each degrees of freedom the energy will be half kT. So kinetic energy of an ideal gas is equally shared among its all degrees of freedom, and along each degrees of freedom the kinetic energy will be half kT, where K is Boltzmann constant, T is temperature in Kelvin scale. Okay. So these things you will require for the calculation. What is the work done by the gas in this process? Work done by the gas in this process. The working substance is taken, I consider a monoatomic gas, ideal gas, from P1, B1, A to B, then B to C, then C to A. What is the total work done in this process? How many processes are there? 3. So in the 3 process, what will be the total work done that we can calculate? First process, A to B. Which type of process? Isothermal. Why isothermal? PV curve slope is constant. See, B to C, which type of process? It is occurring at same pressure. So this is isobaric. Okay. Then C to A, isochoric. But A to B, it's not isothermal exactly. Isothermal curve should be rectangular hyperbola. It's a straight line. It is any general process that is given. And how to calculate the work done? By calculating the area under PV graph. That you can from that you can calculate the work done. Okay. Now see. First I consider this path. There is no other. A to B. What will be the work done in this case? You have to calculate the area of this entire trapezium. Because integral P dV is the work done. So that is the area of this trapezium, and you know the formula to calculate the area of the trapezium. That is work done in A to B. See, volume is increasing. Volume is increasing. So gas is doing positive work. That's why volume will increase. So I can write from this that this height is P2. This height is P1. This height is P1. This height is, that height is P2. So what is the area of trapezium? Half into sum of the parallel sides into distance between the parallel sides. Half into sum of the parallel side means P1 plus P2.
Yes, sir.
And distance between the parallel side means this one. This part is V2, this part is V1. So it will be V2 minus V1. Okay. Obviously in this case, I will write it like this. This one is taken final value, so P2, P1. So this is the work done under the curve. Work done under the PV curve with the volume axis will give us the, this is the area under the PV curve, which is representing the work done in process A to B. Now see, the next process I will draw separately. This is from B, then going to C. So what is the area under PV graph? It is a rectangle now. So we have to calculate the area of this rectangle. Now calculate what is the work done. See, pressure remain constant. This is isobaric process. Pressure remain constant. Only volume is changing. So what will be the work done in WB to C? So at B, the pressure is taken constant. So that is P. What is changing volume? V2 minus V1 or V1 minus V2. Final volume minus initial volume. So V2 is here, V1 is here. Now tell me which one is smaller? V1 or V2? Direction. In that case, pressure at the same horizontal level will not be same. It will be changed because pseudo force will start to act on the liquid molecules, and as a result you cannot say that pressure at the horizontal level will remain same, and top surface of the liquid will not be horizontal if it is moving with acceleration, because in that case if it is moving with acceleration in this direction, liquid surface will be like this, because due to pseudo forces liquid will move in this opposite direction, and as this side will move up because this side will have more pressure, this side will have less pressure. This will occur if it is moving with acceleration. But as long as it is a static liquid, we can consider the top surface will be perfectly horizontal, and at each point inside, if you consider this kind of a line, at every point on this line pressure will remain same value. Okay, that is only for static liquid, remember. Now, if we have some confined liquid, Confined means suppose in a balloon some gas is there and there is no chance of leakage, means the gas is completely confined in the balloon. In this type of a situation, some gas or any liquid, any fluid is there, and we consider one property of this fluid, that is, it is incompressible. Like that inextensible string that we have discussed in case of pulley problems, we consider here the fluid is incompressible, means by applying a certain amount of pressure you cannot change its volume. Then it is called an incompressible fluid. And remember, not only incompressible, we consider another property, that it is confined, means there is no leakage, means no mass of the fluid can go out of this boundary, no mass of the fluid can enter this boundary. Clear? In this situation, if you apply a certain force here, then some pressure will be created at this point. Then at each point of this liquid, the pressure will be same as that of P. Then you can say that at any point pressure inside this fluid, pressure will remain same. So we can say that if I apply some pressure at any point, it is transmitted throughout this fluid in an undiminished magnitude. If the conditions are that fluid should be incompressible and fluid should be confined, in this situation, if you apply certain pressure at any point of the fluid, then this pressure will be transmitted throughout the fluid in an undiminished magnitude. Okay? Because same magnitude of pressure you will get at any point of this fluid, and that is called the Pascal's law. Pascal's law. So for the validity of Pascal's law, two necessary conditions are: fluid should be confined and it should be incompressible, otherwise it will not happen. The pressure is transmitted but magnitude will not remain same, it will be changed if it is compressible fluid. Okay. Now we will see one application of the Pascal's law. This setup is utilized in hydraulic brake, hydraulic jack, any hydraulic devices. This setup is used. Okay. Now consider here two pistons are designed like this, and inside there is a fluid. It is considered as incompressible, and these pistons are completely airtight piston. Airtight and piston, and which can move freely. There is no friction between the boundary of the piston and the wall of the pipe. It is a movable, frictionless, and there airtight piston, means no fluid can escape and no fluid can enter. And we consider a special property of the fluid, that is incompressible. Okay. Now we apply a certain force perpendicularly on the first piston. We consider the area of the first piston to be A1 and we apply here a force F1
We said that.
perpendicular. What will happen to the first piston?
It's giant.
First piston will move down. Suppose here up to this much it will move down.
It should be.
We consider that it is moving down by a distance x 1. It is moving down by a distance say x1. So the liquid is coming down, so the fluid is coming down, so the volume of the fluid is decreased in the left arm. Volume of the fluid is decreased in the left arm. Then in the other arm, volume of the fluid should increase. So let us consider the second piston will move up.
Yeah. Yeah.
By an amount x2 because some force is applying on the second piston now, which has the area A2. I consider first piston we consider area A1. For the second piston I consider the area to be A2. Then since you push the first piston with a downward force of F1, so liquid volume, fluid's volume will be decreased in the left column and fluid's volume in the right column should be increased. Then it will apply a certain force perpendicularly on the second piston of area A2. So second piston will move up. Achha, will the second piston move up by same amount or different amount? Different amount, because area of cross section is different. Only volume should remain same because the fluid is incompressible. So now you can say that this volume that the liquid is decreased in by a volume A1 x1 in the left column. This volume should be equal to volume of the liquid x increasing in the right column. So what is the volume of the liquid increase? A2x2, because this is a cylindrical volume, this is a very flat cylinder. Previously it is a long cylinder of area of cross section A1, height x1. So volume of the liquid decreased in the left column will be A1 x1. Volume of the liquid increased in the right column will be A2 x2, and since the liquid or fluid is incompressible, this A1 x1 should be equal to A2 x2. Then we can write this logic that A1 x1 will be equal to A2 x2. This is coming from the incompressibility. Since it is incompressible, fluid is incompressible, that's why it is coming. Decrease in volume of the liquid in left column will be equal to increase in volume of the liquid or fluid in the right column. This is coming from incompressibility. Now, what Pascal's law will give? F1 by A1 should be equal to F2 by A2. F1 by A1 equal to F2 by A2. This Pascal's law will give this one, that is pressure in the left column will be pressure on the left piston will be equal to pressure on the right piston, because the fluid is incompressible and confined. So pressure created here is transmitted throughout with same magnitude. So P1 A1 should be equal to P1 by F1 by P1 equal to P2, means F1 by A1 equal to F2 by A2. Now see, if I try to calculate F2, it will become A2 by A1 multiplied by F1. Now which is more, A2 or A1? A2? So we can get F2 is greater than F1. F2 is greater than F1. Means by applying a small amount of force, you can actually get a large amount of force. By applying a small amount of force F1, you will get a large amount of force. Means this force is acting perpendicularly. If conservation of energy is violated, then your all this law cannot be correct. So if multiplication of thrust is not consistent with the conservation of energy, then Pascal's law is not true. So you have to check that in this entire procedure of multiplying force, energy conservation is not hampered anywhere. If it is hampered, then it is not possible. What is your opinion? Is conservation of energy obeying this? That by applying a very small force, you can get a very large force in this setup? See, I consider that gravitational force, gravitational potential energy change will be very negligible, because this pipe and all this setup, in this the liquid height is very small compared to the radius of the earth. So I can only consider that gravitational potential energy on both sides will remain same. But what about the energy supplied by the force applied by you and the supplied by the other force F2? That force is doing mechanical work, so it is supplying some energy to the system. So whether these are obeying conservation of energy or not, check. In from Pascal's law, can I write F1 by F2 that is equal to A1 by A2? From Pascal's law, first step, I write F1 by F2 equal to A1 by A2. Now this one is the incompressibility. Since it is incompressible, I can write A1 by A2 is actually x2 by, substitute it in this format. It is giving F1 by F2 equal to x2 by x1. Because A1 by A2 is x2 by x1, so we substitute it in place of A1 by A2. So it is coming F1 by F2 equal to x2 by x1. Then cross multiply both sides. You will get F1 x1 equal to F2 x2. What is F1? Force applied on the first piston, and x1 means displacement of the first piston. So it is the work done on the first piston. F2 is the force on the displacement of the second piston. So work done on first piston and work done on second piston are equal. So work done by force F1 and work done by force F2 are equal. That proves the conservation of energy. Work done means here energy. So both forces are producing same amount of work done, means they are obeying conservation of energy. So Pascal's law is valid and this multiplication of thrust is also valid. Because high force displacement is more, low force displacement is large. So that's why product will remain same. That is work done. Thus it is obeying the conservation of energy. So multiplication of thrust is a direct consequence of the conservation of energy. So it is a correct law.
Yeah, I'll see it.
Okay. See, now we will introduce another case. Suppose a solid body is immersed in a fluid. Okay. Then it will displace some amount of the fluid to occupy certain volume. So if it will displace certain amount of fluid, then this displaced fluid's weight of the displaced fluid will apply a force on this solid body in the opposite upward direction to move this body out of this fluid. Okay, that particular force is called the buoyant force or upthrust. So there is a liquid in a container. I want to put a solid body inside the liquid. Then if I push it inside, or if I drop the body inside the solid liquid, then liquid or the fluid will try to move it out, try to throw it out. Why? Because the solid object is occupying some volume inside the liquid or the fluid, then it will displace some amount of fluid, and displaced fluid has some weight. This weight is creating a force of equal magnitude in the upward direction to move out this solid object. This particular force is called the buoyant force or upthrust. Okay. Now, upthrust of the body is acting in the upward direction and weight of the solid body is acting in the downward direction. So, are they action and reaction? No, because they are acting on the same object. And don't even think that if the body is floating and weight of the body and upthrust are equal, still they are not action and reaction, because action and reaction cannot cancel each other. Okay, so these are completely two different forces given by two different agents. Weight is given by earth attraction, buoyant force is given by the fluid on that solid. Now, I will ask you about a certain situation. Suppose there is this kind of a box. It is half filled with water and remaining half is filled with air. Half filled with water and remaining half is filled with air. Okay. Very small air is there, this much. Now consider a solid cork, a solid cylinder, cylindrical cork is floating. A solid cylindrical cork is floating in this. It is half immersed in water and remaining half is in air. Exactly half portion of this cylinder is immersed in water and other half is in air, and it is floating completely, means it is at rest. Now you are preparing a pinhole and using a suction pump, all the airs are evacuated from this chamber. Only air, not the water. Only air is evacuated from the chamber by using a suction pump. What will happen to the immersed level of the cork? Will it immerse more in the water? Will it immerse less in the water? Or will it immerse same as before? Means half volume is immersed, more volume is immersed, or less volume is immersed. If the entire air is taken out, and it is considered that air has very negligible pressure when it is inside. Air pressure inside you can neglect.
Okay.
Three possibilities. Will the volume of the cylinder, initially how much volume is immersed? V by 2. If I consider volume of the cylindrical cork is V, then V by 2 is immersed initially. Then when you evacuate with all the air from this, what will happen to the immersed volume? Will it be equal to V by 2? Will it be less than V by 2? Or will it be greater than V by 2? And it is given that air pressure on the cork when the air is inside, that is negligible. What? Remain same. Then you can say that air is not a fluid. Air is a fluid. Air is fluid. So air can also exert buoyant force as well as water. So when air is evacuated, buoyant force of air is missing. See? No? Air pressure is negligible, it is mentioned. Only the buoyancy of air has to be taken into account. It will immerse more in water. How? See, previously when air and water both are there, it is floating, means it is at rest. So how many materials are applying upthrust on this? Water will apply as well as air will apply. So buoyant force of air plus buoyant force of water, that is equal to weight of the solid cylinder. Means floating body is always weightless, net force 0. So upward direction there are two forces. One is BA, another is BW. And downward direction there is weight. Okay. Now all the air is evacuated. So which force is there only? Given by water. So write it as BW prime. BW prime now in the second case. How much, what weight of the cylindrical cork will remain same? That is not affected. So now tell me, if air is so equate these two, then you will get BA plus BW. That is equal to BW prime. Then can I write BW prime minus BW? That is equal to buoyant force of air. Now tell me whether buoyant force of air is positive or buoyant force of air is negative. All the buoyant force are in the opposite direction, so it should have a positive value. So which one is greater? So BW prime should be equal to, you should be greater than BW. Because previously air and water both are applying buoyant force to balance this weight. Now only water is exerting buoyant force to balance this weight. So buoyant force of water should be increased now, because it will balance the entire weight alone. Buoyant force of air is not there to help. So BW prime is now greater than BW. Can I write this one is volume immersed, volume of the cork immersed into density of water into G, volume of the immersed portion into density of water into G. So more volume will be immersed now, because if it is immersed more, then only volume immersed will be more, then only buoyant force of water will increase to balance that W alone. Previously, buoyant force of air and buoyant force of water together balances W. Now air is evacuated, so buoyant force of water has to be increased to balance W. And when buoyant force increases, if the object immersed, more, so it will immerse more volume will be inside. Okay. Okay, for today, enough for today. So we will discuss in tomorrow's class, remaining part.
Experience of what